interesting sort of second order low pass filter structure, in this case built with op amps. Now, the original core of this structure is something known as a Diff2 structure in transconductance amplifiers. But it turns out that if you can build something in one topology, you can always move it into a different space. And so that's what this circuit's about. And by doing so, it actually allows you to get a little bit of different intuition of what's going on here. And unlike a transconductance amplifier version where I would change the bias currents of the amplifiers, here I just decided to change the capacitors. In fact, decided to just make one element is basically a low-pass filter with a gain of 1, which is very similar to that initial stage. Of course, inverting gain. And then I have a differential I have an amplifier in a differential configuration. So you'll notice that I have both R and R coming into the plus and minus terminals, and then in the feedback and to ground is the C1 terminal. This is what you would expect in terms of getting sort of a difference configuration between the output voltage under the plus terminal and the input voltage onto the minus terminal. And so what's nice about it is these are first order structures. The first one is basically a straight integrator. So I'd expect it's V1 times SRC, because R and C1 is what the core structure is. And it's going to be the difference of V out minus V in. If you're not sure how to get that exactly, you could actually just write, KCL at this node and this node, solve this out knowing these two nodes are equal. I'm assuming all ideal op amps. The second one, this is a low pass filter, gain of 1, so I would expect this is going to have R and C2, and then minus V1 because it's coming into the minus terminal. Again, if you're not sure how to do that, you just write KCL at this node, realizing this node's basically a ground, and you can pretty much solve it straight up in terms of what the time constant behavior is, knowing that, of course, C1 and C2 are, I think of them in the Laplace space. That's why there's the S in front of it, because it gives you a Laplace kind of transformation. Well, taking these two equations, I can then end up substituting the V1 into here. That inverts it, the V out comes on this side, the V in stays there, and I get this structure, which then gives me a very straightforward function in terms of my transfer function. Second order, it turns out that R squared C1 C2 gives me my time constant. Cool, right? I've already got that one. And then R C1 is then going to be my tau over Q. And so I can get Q as a tau over RC. RC1, and then when I push this through, that actually gives me something very nice, which is the square root of C2 over C1. So you're like, this is awesome. Okay, so it's like, wait, I can choose different caps, and I get different responses. That's kind of a neat circuit to try to build. In fact, if you want to think about how this looks and put some values in it, imagine R is 160 k ohms. And then for the capacitors in nanofarad, if there's 1 nanofarad, my time constant is 0.16 milliseconds. A very convenient number to pick because it means that my corner frequency is 1 kilohertz. And so you think, that's awesome. I can start to work with that. This is a low pass structure. The gain is going to be 1. So I get sort of 1 here. And then I can actually see this for different Qs, and it falls off. And I can also then see the phase response as well. So really nice that I can see these different aspects. But of course, Q equal to 1 is when I've got 1 nanofarad, no problem. Interesting thing happens though if I start to change what my values are for C1 and C2. If I do C1 as 0.125 and C2 is 8, I get a Q of 8. So it gives me the Q of 8 cases. If it turns out to be 8 and 0.125, then I get a Q that's 0.125, and I get this sort of interesting Q that now actually has 2 real roots and is well separated. But it's kind of nice to be able to say, here's another structure which I can look at and then be able to design and work with, and be able to select what kind of Q do I want, and also be able to set up my corner frequency as a result.